All right, grade 11s. Well, good afternoon. I know you haven't heard a lot from me this week. It's been a really busy week, actually. So I hope you're doing okay with this heat capacity assignment. No one's really been asking a lot of questions, but yeah, make sure you get the textbook homework done too. We're almost done the unit. I thought we'd have a quiz this week. I have a little lab activity as well. So if you could take a look at those couple of things, I will post them tomorrow. Quiz, I was thinking maybe on Thursday. Okay, just a few questions, method of mixtures, and a few other things. Just on heat, on the assignment I gave you, textbook homework. But anyway, there was a couple of textbook homework questions here on efficiency, so let's get to it, and I will help you do these questions. The first one is page 143, number 5. Okay, it says a construction worker uses a rope and pulley system to raise a 27 kilogram can of paint 3.1 meters to the top of a scaffold. The downward force on the rope is 3.1 times 10 squared, and the rope is pulled for 3.1 meters. All right, so question A. I'll switch back to black here. Find the work done in raising the can of paint. Well, work is just equal to force times displacement. So you're pulling down on the rope and with a certain amount of force. So it's pretty straightforward. You're going to go 310, which is this number right here. The book always puts things in scientific notation, and that's their displacement right there. Okay, so it's just going to be 310 times 3.1, which is 310 times 3.1 equals 961 joules. All right, so that's how you do question A. Question B, okay, how much useful work is done? Well, you see, the useful work is how much energy the object gains because you're lifting it, and that is gravitational potential. So that's the useful work that it gains, okay? That's the amount of energy it gains, which is equal to the useful work. Okay, so that's going to be 27 times 9.8 times 3.1. And I get 212.66. 212.66 joules. Okay. Now, the next question says, what is the efficiency of the system? Well, we can see here that this is the energy out, is the useful work that's done. This is the energy in, and you can see there's a difference. So the efficiency is just equal to the energy out divided by the energy in times 100%, right? That's for percentage efficiency. So if I just take those numbers and go 212.66 divided by 961, I get 22% approximately. Okay, is the efficiency of the system. Okay, so anyway, that's it. Oh, I'm sorry, question C. That is question C, pardon me, that's C right there. Question D, why is it not 100%? Well, nothing ever is. It's simple, really. The answer is friction in the case of a rope and pulley system, and that creates waste heat. In this case, quite a lot, actually. That's one of those squeaky sort of pulleys, I guess. There's a lot of friction there. Normally, pulleys would be more efficient than that, but you can't get 100% anyway. There's always some friction. And so that's the answer to question D. All right, next question. A parent places a bottle containing milk. Now, that milk has the heat capacity of water. Okay, it's mostly water anyway. And then it's mixed with water. Okay, compare the average kinetic energy. Well, in question A, temperature is a measure. I'm just going to write it, of the average EK. So that's the definition of temperature. So which one has the higher temperature? Well, the pot containing the hot water, obviously. Okay. All right. Now, here's the thing about thermal energy. Okay. So therefore, the pot is higher. Or has. Doesn't sound right. Okay. the pot has a higher average. Okay. Question B. Compare the thermal energy. Thermal is a total. The pot has more mass, and it's hotter, and therefore it has a higher thermal energy. Okay, and that's how you do question B. Now, will the heat stop transferring for the water? And the answer is in question C, when it reaches equilibrium. When you mix these two things, at the same temp, the energy exchange stops there. Okay. Well, I mean, I guess there's still some exchange going on, sort of back and forth, but there's really no more transfer directly one to the other. It's more, you know, you might get some molecules colliding that are transferring energy back and forth, but you're maintaining the equilibrium, so there's no net change in temperature then after that. All right, question 6. The nuclear generating station located in Pickering has one of the largest. It's one that's rated at 2,160 megawatts of electrical power. How much electrical energy in megajoules can the station produce in one day? All right, well, power equals energy over time, right? So therefore, energy equals power times time equals, let's just leave it in megawatts, 2160, okay, times the amount of time it's in a day, times 24, times 3600. 24 hours a day, 3600 seconds in an hour, okay? So basically just multiply all that out, 2160 times 24 times 3600 equals, and I get 1.87 times 10 to the 6. So this is equal to 1.87 times 10 to the 6, not joules, megajoules. Okay, had we converted it into watts instead of megawatts, then it would have been in joules, but so we would have got a much larger number. We would have gotten 10 to the 12 instead. So anyway, that is your answer right there. Okay, so there you go. That is a couple of questions from the textbook, and I'm going to post this video, and I hope that was helpful. Okay, talk to you soon.